Hello, stat students. Today in 6.1b, we are going to talk about another random variable known as a continuous random variable. Last time we talked about discrete random variables. Discrete random variables commonly arise from situations that require you to count something, and I had mentioned that. Situations that involve measuring something often result in a continuous random variable because you have an interval. A continuous random variable x takes on any value in an interval of values. The probability distribution of x is described by a density curve. So instead of having that table where you had your x values and the probability for a continuous random variable, the distribution is described by a density curve. And so here we get into like your normal distributions. Whenever we have our normal distributions, we can use our normal CDFs to find probabilities. And so we're going to be using our calculator quite a bit. The probability of any event is the area under the density curve and above and below the value of x that make up the event. So basically, we are going to look at something like this. So this is not a very good normal distribution, but so here's our, maybe you have this, and you don't have to say that's the mean, but we're looking for this probability to the right of that value. Or we might have something like this. It's not very good either, but it's okay. And we might be looking at finding the probability here. So we're not finding a specific value. The probability model of a discrete random variable assigns a probability between 0 and 1 to each possible value of x. However, for a continuous random variable, and we'll call it y, just to differentiate between the previous one that I mentioned, has infinitely many possible values. All continuous probability models assign probability of 0 to each individual outcome. That's why we don't use, if you've ever noticed on your distribution menu of your calculator, you go into, you press second and you hit vars, you will get to that distribution menu. We don't use, in this case, a normal PDF because a normal CDF is a cumulative distribution. Only an interval of values will have a numerical other than 0 probability. Might not make much sense now, but it will when we do our examples. So we have two examples in this section. The first one is the heights of young women. So the heights of young women closely follow the normal distribution with the mean mu of 64 inches and standard deviation sigma of 2.7 inches. This is a distribution for a large set of data. Now choose one young woman at random. Call her height y. If we repeat the random choice very many times, the distribution of values of y is the same normal distribution that describes the heights of all young women. Find the probability that the chosen woman is between, the chosen women, should be woman, is between 68 and 70 inches tall. Okay, so here we have our mean. So sketching that in. The mean is 64 inches. And our standard deviation was 2.7 inches. And we are asked to find the probability indicated with the question mark. And that is normal distribution. We didn't even have to draw the mean in, but I went ahead and drew it in. So we are asked to find the probability that the chosen woman is greater than or equal to 68 and less than or equal to 70. So between 68 and 70 inches. And so we are going to, this is hopefully bring back memory. So you go to second, hit the second key, then vars, and then you're going to use normal CDF. And then you are asked for your given prompts, and you have to write down what your values mean. So the first one is, what is the lower bound? And the lower bound is your left bound value, which is 68. So 68 is your lower bound, and you have to indicate that it's lower bound. Your upper bound is 70. Your mean is 64 inches. And your standard deviation is 2.7. Must label this for full credit. And that'll give you a probability of 0.0561. And then let's just go ahead and interpret that as well. Or actually just write it out as a sentence. But the probability that a randomly selected woman's height, because you're in essence interpreting this, is between 68 and 70 inches is 5.61%. Right. We'll do one more example. This one is weights of 3-year-old females. The weights of 3-year-old females closely follows a normal distribution with a mean of 30.7 pounds and a standard deviation of 3.6 pounds. Randomly choose one 3-year-old female and call her weight X. Find the probability that the randomly selected 3-year-old female weighs at least 30 pounds. So here you have to you have to fill in the numbers for your normal distribution. And a lot of times you get points for this, especially if it asks you to draw it. And it also helps you determine if your answer is a valid one. So we're going to put in our mean, which is right here, 30.7. And to that, we're going to add 3.6 pounds, and because that's our standard deviation. So this one is 34.3. Add 3.6 again, 37, or 3.6 again, so 37.9, and then 41.5. On the other one, you subtract, so you have 27.1, 23.5, and 19.9. And we are asked to find the probability that the randomly selected female's weight is at least, so greater than or equal to 30 pounds. So we're going to use our normal CDF. And then we are going to fill in our information in that particular, for the prompts. Our lower bound is 30. We need to draw this information in too. So at least 30 pounds. So let me find 30, just a little right here. And so we want this probability. Upper bound is 100. Oh, we pick a really large number because our largest number to the right is 41.5. So just pick something bigger than that. So upper bound. Our mean is 30.7. And our standard deviation is 3.6. And that gives us probability of 0.5771, probability that a randomly selected three-year-old female weighs at least 30 pounds is 57.71%. And those are your notes for 6.1. Have a great day, stat students.